Good morning. So welcome to our final stream for sampling and experimental design. Today I have some slides up and I will be doing some review with you. And as part of this last stream, as you may have seen on the thumbnail, there will be some prizes today. So I'll be asking some questions along the way, and there will be at least 3 or 4 chances for you to win your choice of drink and donuts, which I will provide as soon as next time you're on campus after campus opens. So make sure you are ready to answer questions in chat. Okay, so on this first slide is simply a list of all the topics that we have covered in this course. And so this is just a very brief outline. So so I've kind of blocked this into three categories. Okay, so the 4 topics at the top were tested already on midterm 1. Okay, and then so everything in blue has not been tested yet. So that's starting from cluster sampling to the end of the course, which was our very last model on Wednesday on factorial design with blocking, 2-factor with blocking. Okay, and so what these review slides will focus on is the last part. So the points you see in blue and bolded. So those will be covered in these review slides. Of course, there have been other 2 sets of review slides that you can also look at to help review midterm 1 and midterm 2 stuff. But I'll wait till the end to give you more information about how the final assessment will be structured. Okay, so with that in mind, let's jump into a review. And so I'm going to cover these bolded points in today's slide set. Okay, so the first new topic in this part of the course was taking the completely randomized design, the CRD, and extending it to have an unbalanced number of replicates. And so what that means is it's a CRD, but you can have a different number of replicates per treatment. So this model, that models the response in the ith treatment and the jth replicate as the overall mean plus a treatment effect and the residual. Residual is always independent normal, mean 0, variance sigma squared. So the difference with the balanced CRD is we're now allowed to have a different number of replicates, so that's R sub I. And so this could be for any number of reasons. You might have, as in your homework, you might have lost some units may have dropped out or become unavailable, and so even you might have started with a balanced design, but for whatever reason you may have lost some units. Okay, so how does that change the analysis? Well, to a large extent, it's very similar, and so there's just a few differences compared to the CRD, which I will point out. The first difference is in the constraints. Now if we want the overall average of all the units, so expectation of y bar dot dot, if we want that average to equal mu, then now the constraint required on tau is this one. So it's summation tau I, but they need to be multiplied by the number of replicates r sub I. Okay, and you see this constraint is just a generalization of the CRD because if all the RIs are the same, then they're just R, so that's a balanced case. If all of them are R, then you see that you can simply divide by R and you get the constraint for the balanced case, which is summation tau I equals 0. Okay, so that's just a generalization of that. But the interpretation of all the parameters are the same. So mu is the expectation of the overall average, okay, and then tau I is the treatment effect, which measures the change in the mean as a result of applying treatment I. Okay, so therefore the average of treatment group I is the overall mean plus the treatment effect, mu plus tau I. Okay, so that's the setup in the unbalanced case. And so we use the unbalanced case to also illustrate how we do tests of contrast. So this is a good time to quickly review what is a contrast. So it's a linear combination of treatment effects. And so the treatment effects are these tau i's, and the contrast specifies certain constants, ai, such that they sum to 0. So this is a linear combination of treatment effects. So they're all, so it's simply constants times treatment effects, depending on which treatments or set of treatments that we want to compare within that contrast. Okay, key thing is we're only testing one linear combination at a time using a contrast. And so that's why when we're only testing one equality, that's done using a t-test, compared to when we're testing multiple equalities, that's when we get our ANOVA f-test. Okay, so how do we estimate the contrast? So it's the same way. So you estimate theta with theta hat. So all you have to do is plug in the tau I hats, so the estimated treatment effects. And because of the contrast, this property that the summation ai is 0, plugging in tau I hat actually simplifies to simply yi, the yi bar dot. So that's the treatment mean. Okay, so that actually simplifies because of this summation, because of this constraint here on the AIs. Okay, so you take each of the treatment means and then multiply by a constant and sum. That's the estimate of the contrast. And the only difference compared to the completely randomized design with balanced number of replicates is that the y bars, so these treatment means, might now be averaging over a different number of replicates, but that's okay. All we need here is still the average. All we need here are still the treatment means, no matter how many replicates were recorded for that treatment. Okay, there's a question that asks why do we require summation ai equals 0? So that's by definition of a contrast. So that if there is nothing going on, so if all the taus are, if there is nothing going on in the taus, that's going to sum to 0. And usually we test. Okay, so usually the way we test contrast is we ask whether that contrast equals whether that contrast equals 0. And so when the coefficients equals 0, basically your linear combination of the treatment effects. So these coefficients. So basically you're balancing out such that the weighted sum, if all the treatment effects there are actually equal, simply sums to 0. So that's usually the way we set up test of contrast. So we might be asking whether tau 1 equals tau 2. That would be expressed as a contrast tau 1 minus tau 2 equals 0. So the coefficients there are 1 and minus 1. That sums to 0. While we in this course have not tested anything, for example, we haven't tested anything like tau 1 equals, let's say, 2 times tau 2. So that would not fit the definition of the contrast that we're considering here, because 1 minus 2 is not 0. Okay. So once we set up the contrast, we can use the corresponding t distribution for doing the formal hypothesis test and to calculate confidence intervals. Okay, so you look at this expression. So on the top is well the estimator for the contrast minus what your minus the true value under the null hypothesis. So often we're testing whether the contrast is 0 or not. So often we're going to be plugging in 0 here, and then we use the formula for the contrast estimate to fill in the numerator. So that is the value so after you plug it in, you plug in theta hat to get the estimate of the contrast, and in the denominator is the standard error of the contrast. Okay, so just to remind you, there's a couple pieces here. So first you need sigma. Okay, so the estimate of the residual standard deviation. So often, instead of calculating it directly, now that we've learned ANOVA, we can pull sigma from the mean square residual from our ANOVA table. Just remember it's sigma, so in other words, it's the square root of sigma squared, the estimate of it. Okay, and then and then here is the part of the standard error associated with the contrast and the number of replicates. From linear combination of normals, we know that we need the square of the contrast coefficients divided by the number of replicates for that particular treatment. Okay, so now they can potentially be different. So R sub I, sum them, and then square root. So this whole thing on the bottom is the standard error of the contrast. So here, so from this t distribution, you can then get your hypothesis test. So this would be your t obs after you plug in the values. And if you need a confidence interval, then you simply do your theta hat and then plus minus the critical value times the standard error, which is this whole thing in the denominator. Okay, so that's contrast, and then here's the corresponding ANOVA table. So it looks very much like the balanced case ANOVA table, except instead of R, you have R sub I. Okay, so that's the ANOVA table, so make sure you know how to fill in the quantities from for example, if you're given some incomplete information, that you know how all these quantities are related to each other. Okay, next topic we had was randomized block designs. And so remember, we focused on the case where there is just one replicate per block. So in other words, there's one unit assigned to each block and treatment combination. And so ij is ith treatment and jth block. And so instead of R replicates, we now have B blocks, and therefore we have an associated set of block parameters beta j here. Okay, so again with the usual way to interpret these, we have the overall mean response and then the treatment effect and the block effect with these two sets of parameters and their corresponding constraints, which is they both sum to 0. In terms of assumptions, remember that we're assuming it's the same sigma squared for all the units, and we're also assuming that now that we've seen the difference between interaction models and additive models, we see that it's tau I plus beta j. There's no interaction here, so in other words, we're saying the treatment effect and the block effect is additive. Okay, and in other words, there's no interaction between treatment and blocks. That's by assumption in this model. And it's additive in the sense that the treatments would have the same effects no matter which block you're in, because you can just add the two effects together. So the key new idea in the sum of squares decomposition is that there's now a term for blocks in the sum of squares decomposition. Okay, so the treatment sum of squares stays the same. Instead of R for replicates, we just now have B for blocks. The total sum of squares stays the same. So what happened is that the residual sum of squares compared to the CRD is broken down now into a block sum of squares, and then you have the residual after accounting for blocking. So this is the new residual sum of squares. So if we lay it out as the equation for decomposition, then total sum of squares is now decomposed into treatment plus block plus residual, and so these are the three terms we saw on the last slide. So make sure you understand how this decomposition was derived, and that indeed this is an equality, that indeed all the cross terms are 0, and so it's these three sum of squares terms actually adds up to the total. So as I noted, the treatment sum of squares and the total sum of squares does not change compared to the CRD case. So what happened is that the residual sum of squares for CRD is now broken down into these two parts. Okay, and so after we add the blocking variable, what used to be the residual sum of squares gets broken down into the block part, and then the residual part now that we've accounted for blocking. Okay, and so that gives some intuition as to why blocking helps in terms of detecting differences between treatments. Okay, so you see the treatment sum of squares has stayed the same, which means the treatment mean square is also the same when we go from CRD to RBD. So in other words, the numerator of the F statistic is the same whether you're looking at CRD or RBD. So what's changing is the denominator of the F statistic. And the denominator of that, as we know, is the residual mean square. Okay, and so therefore, if you have a good blocking variable, then the block sum of squares is large, and so that means you're leaving much less variability in the residual sum of squares, and therefore a much smaller residual mean square. Okay, therefore sigma squared hat can potentially be much smaller when you have a good blocking variable. Okay, and so therefore that can reduce the mean square residual, and so that can increase the significance of your F statistic, which makes it easier in turn to detect differences among treatments. Okay, so this just puts everything in the ANOVA table, so now there's an extra row for blocks that has the block sum of squares. So because of the sum of squares decomposition, usually the easiest way to get your residual sum of squares is to simply get the treatment and block sum of squares and then subtract it from the total. Okay, so now we know that there are two possible F tests that you can do here. So usually the one we care about is the F test for the significance of treatments. And so that's this one here. It's the mean square for the treatment divided by the residual mean square. So that's usually the F statistic we use to ask the question of whether there are any significant differences among treatments. Okay, so now that we've seen many of these ANOVA tables, the easiest way to remember the degrees of freedom in your F distribution is simply you just look horizontally in the same row. So that's your numerator degrees of freedom for the corresponding F statistic. So numerator is t minus 1. And the denominator degrees of freedom is always the residual one. So that's t minus 1 times b minus 1 for RBD. Now, we've also learned that, well, we can also test for the significance of the block. So you could also compute an F statistic for the block by taking the mean square for block divided by the residual mean square. Okay, so that gives you another F statistic that we could also look at. And so if you want to ask whether there are significant differences among the blocks, then you would use the corresponding F distribution. So look over here, the degrees of freedom in the block row, so b minus 1, and then residual degrees of freedom. So if you now look at this table, we pointed out that it's especially clear when we do this analysis in R that there's no mathematical difference between treatments and blocks. They're mathematically the same. So the only way we know which one is the treatment and which one is the block is really a matter of interpretation. So what that means is we ask, well, which factor or which variable was something that we actually set up as part of the experimental investigation? Well, that would be your treatment and or factor. Whereas block is simply a characteristic of the units that can help explain the response, but we're not doing experimenting that we're not doing the experiments on. Okay, so that's how we can tell the difference. It is a conceptual or interpretation difference rather than a mathematical one, the difference between treatments and blocks. Okay, and so I've kind of talked about this already, but this is an important point that's worth emphasizing. So why do we do blocking? So fundamentally, how we set up blocks is we're dividing our experimental units into groups. Okay, and these groups share some characteristics. And so it's going to work best when this characteristic helps explain some of the variability in the response. And as we mentioned, that will help reduce the residual sum of squares. Okay? And the reason we call it a blocking variable rather than a treatment is because it's not part of the experiment. We're not changing the input for the blocking variable, okay, but it's nonetheless associated with the response. And so generally we put it in to help explain the response, but we're not interested in particular in the block effect itself. Okay, so remember the old saying, so we block what we can, so we know characteristics about the units, then we should use that as a blocking variable for the reasons we explained. And otherwise, we use randomization to balance out the effect of all the myriad of potentially unknown variables that could also affect the response. Okay, so the practical effect is that it can allow us to more easily detect differences between treatments if there is a treatment effect, okay, because it reduces the residual sum of squares. Okay, so from the last table, you should be able to see how the ANOVA results changed when we add a blocking variable. It changes the residual sum of squares. It breaks off part of the residual sum of squares into the piece for the blocking variable. Okay, so in practice, there's been several practical scenarios that you should have looked at or will look at in your practice sets that ask you to identify possible blocking variables. So just think practically what might be useful as a blocking variable, and then how to set it up if you were to do an experiment in practice. Okay, and so finally, how do we check assumptions for RBD? So we mentioned two techniques, which are both visual. So we can do things like a normal QQ plot to ask whether the residuals, so in other words, the RIJs roughly follow a normal distribution. So that's a QQ plot, and then you can also, just much like in regression, you can make plots of the residuals themselves to see that they're roughly symmetric, around 0, and normally distributed. Okay, so now we move to factorial design with two factors. Okay, so the key part of the new part of the setup is that we're now assuming that T treatments are composed of a combination of two factors. So you have TA levels of factor A, T sub B levels of factor B. And so the overall treatments are coming from their combination. So there will be a possible TA times TB number of treatments. And we learned previously that we can use the CRD to analyze all the treatments separately, and so this is the CRD model we've previously seen. And so what this factorial design model with interaction does, it simply takes this old CRD model and rewrites it. So it takes the treatments, so the tau i's, and breaks it down into the three sets of parameters, alpha, lambda, and gamma, where alpha and lambda are the parameters for the main effects of the factors, and then gamma is the interaction. Okay, so that simply takes the tau i's and then breaks it down into these three components. So a lot of the theory from the CRD we can carry over, and that's what made some of the mathematics easier to handle. So that the key fact that we used when we looked at this model was remembering that excuse me, the number of free model parameters has to be the same in both models, because they're just two ways of writing the same model. Okay, so that allows us to get the degrees of freedom for the interaction model much easier. Okay, so let's just do a quick recap of why we used the interaction model. So here's a few points to remember. First is it allows us to test for interaction. Okay, so the hypothesis test for interaction is to ask whether all the gamma parameters, so those are the interaction parameters, are 0. So if they're all 0, then that means there's no interaction. And so this is the hypothesis that we test formally using generally the ANOVA F test for interaction. Okay, and so remember also that we say that the factors interact when the effect of one factor depends on the level of the other. So in other words, we can't just add together the two effects. Whether factor A has an effect or the size of the effect depends on the level of factor B. And so that's factor interaction. Okay, so when there's no interaction, then we say that the model can be reduced to additive effects. So you simply be able to add together the effect of A and B to get the corresponding average for each treatment, and that's the additive model with the interaction parameters removed. So when this interaction hypothesis involves more than 2 levels for any of the factors, then we can do that using an ANOVA test, because it means testing whether multiple gammas are equal to 0. But in the special case, where there's only 2 levels of A and 2 levels of B, then the interaction can be expressed as a contrast. And you were asked to verify that on your final homework. There was an example where you should be able to find that when there's just one possible interaction, well, because there's only one equality being tested, that can be done using a contrast t-test, and you should get exactly the same p-value as when you're doing the corresponding ANOVA f-test for one interaction. Okay, so now we're going to do a quick example, and so this will be your first opportunity to win your choice of drink and donut, or if you want, drink and choice of poutine. Okay, so the first one is simply a participation raffle. So I'm going to pick a winner. Actually, I'm going to pick 2 winners randomly from chat if you answer this question. So consider this experiment where we ask people to, let's say, evaluate how tasty fries are with the following options. Okay, so this is a 2-factor experiment. Okay, so the 2 factors are whether you want to add ketchup or not, and then whether you want to add gravy and cheese curds or not. So basically, it's so there's two factors, and so 2 times 2, there are 4 possible treatments. Okay, so that means if we write them out in terms of what we understand about fries, these would be the 4 possible treatments. So the first one is you have neither, so that's just plain fries. And so treatment 2 is, well, let's put ketchup but no gravy and cheese, so that's, well, your typical fries with ketchup. And so if you do gravy and cheese but no ketchup, then that's usually what we call also known as poutine. And finally, I don't know what to call this last one, because generally I don't usually put, or haven't usually seen people put both ketchup and gravy and cheese together on fries. So let's call that ketchup poutine. So your first task is to tell me which of these 4 options you consider the tastiest. So you can tell me in chat, and I will draw 2 winners. So let's see if my intuition matches what you guys think about which is the most tasty. Okay, so I'll give you a few seconds to do that. Okay, so so far I'm seeing a lot of 3s. So 3 is regular poutine. So that's very Canadian of us. Okay, so there's 1 vote for option 4 and 1 vote for option 1. So that's plain fries, and then Stanley likes the loaded one with both gravy and ketchup. How does that taste like, by the way? I don't know. All right, any other responses? I'll give you guys about 15 more seconds. Okay, so I think in terms of ranking, so I think overall you guys consider option 3 to be the tastiest. And so followed by a couple of votes for option 2, and then I think only one vote each for option 1 and 4. Okay, so while I was making these slides, I made a guess that I think we got essentially the similar result here. So just to have some numbers to work with, I made this table. Suppose the experiment was we make 32 poutines. Well, I guess they're not 32 actual poutines, but 32 fries with stuff versions. Okay, so 8 of each type, and then suppose the experiment was to ask volunteers to score them in terms of deliciousness, so higher is better. And so I kind of intuitively ranked them. I thought 3 would be the highest, so that seems to be the consensus in chat. So I gave it a score of 7.06, and then followed by 2, which would be the typical ketchup with fries, and then I don't know, and then kind of a tie between maybe plain fries and the overloaded fries with both ketchup and gravy. Okay, so there's the hypothetical table. So suppose each of these numbers is the average of the 8 people who were assigned that treatment, and so they gave a score 1 to 10 of how delicious it was. Okay, so those are numbers, and so we learned in this part of the class that we can make an interaction plot using the treatment means. Okay, so in other words, I'll take these 2-factor combinations and then put the 4 points together like this. Okay, so here's the interaction plot for those 4 treatment means. Okay, so on the x-axis is gravy and cheese, whether we have yes or no, and then ketchup yes or no, and so this shows the 4 treatment means. So the lines are very non-parallel because the hypothesis, or at least I'm guessing, that having one either ketchup or gravy does improve the fries, but then maybe having both is overload, and so that might actually decrease the average score. So one key point to remember when we have interaction plots is that when the lines are not parallel, that suggests there is interaction, but remember the variability around these means is not shown in the interaction plot. So in order to actually test it, we would have to do a formal hypothesis test, and that would depend on whether how large the residual mean square is, right? So that would be a key component of the test, is how large the sigma squared hat is, and that would play into determining whether the apparent visual interaction is actually significant or not. Okay, so are you ready for this next question? So first, correct answer in chat will win a drink of your choice, and either a donut or a poutine of your choice after campus reopens. Okay, so this is the question. So let's rearrange the treatment means in this way. So here's a table. So I've rearranged it into a 2x2 table. And so here is so you have no and yes for ketchup and gravy respectively. Okay, so here are the 3 numbers I just copied. So 4.44 was the average for neither, and then 6 was the average for ketchup, no gravy, and then 7.06 was the average for gravy. I think I actually messed up the labels, but that's okay. That doesn't affect the question. So the question is, if the model is additive, okay, so if there is no interaction, what number goes here in this blank? Okay, so go ahead and think about that, and then type your answer in chat. First correct answer wins a prize. Okay, so to clarify, I want a specific number. So don't give me a range. If the additive model is correct, so in other words, we're additive effects, what would be the value of the blank if the model is actually correct? Okay, we have a winner. 8.65 is correct. Okay, so all right, so you can send me an email later so I know who you are. Okay, so how do we get 8.65 here? Is well, if the model if the model is additive, that means we can add together the effects. So in other words, if you look at this table, we're gaining. So if you're going from nothing to ketchup, so this is actually a mislabel. I think 6.03 was ketchup. Yeah. So going from nothing, so adding ketchup adds this difference. So the effect of the additive effect of ketchup would be 1.59 units. Okay, so that's going from no ketchup to ketchup. And then the effect of adding gravy, okay, so is this difference. So the gravy effect is 2.62, okay? So that's the difference between 4.44 and 7.06. Okay, so if there is no interaction, then we can simply add together the effects. So in other words, the effect of adding ketchup would be the same as whether you have gravy or not. So the difference here is 1.59. So in other words, we would add 1.59 to the 7.06, which is 8.65. Or alternatively, remember, you can think of it the other way as well. You can say, okay, let's add ketchup, so that goes from 4.44 to 6.03, and then let's add gravy, so that's going to add the difference between these two numbers. So you're going to take 6.03 and add this difference, 2.62, and so you would get 8.65 again. All right, so there's only one possible interaction here. And so if there is no interaction, then this number would simply be add together the effect. You gain the same amount for ketchup whether you have gravy or not, so 8.65. All right, so when there is interaction, then it's not as simple to interpret the main effects, because in the numbers I actually made up for this example, whether the effect of gravy depends on whether there's ketchup or not. And so that's when there is interaction, and so it's not as simple as simply taking the additive effect and interpreting separate additive effects. Good. All right, so taking the the ANOVA for this case now, we learned that we can take the treatment sum of squares and break it down into the three components for the two main effects and the interaction. So usually before we do that, the first thing we test is we use the CRD ANOVA table to test whether there's any difference among the treatments. And if there is, then we can follow up by constructing a second ANOVA table that breaks down the treatment sum of squares into three components, and from there we can ask whether we can test for whether there is interaction. So make sure you review this decomposition and know how to work with those ANOVA tables, and that you know what are all the different f-tests that we can do using those ANOVA tables. Okay, so here is just the lumber ANOVA table. I just printed it again here because I want to emphasize one other point. Okay, so here just to remind you, there was factor A. First row is factor A, second row is factor B, and then the third row is the interaction. Okay, so that has the corresponding degrees of freedom, and then we've seen this test before of hypothesis whether there's interaction between the load applied and which test is being used. Okay, and so the F value we got was 0.12, so the interaction is not quite significant at, say, the 5% level. So in other words, the test we use and the load level applied doesn't significantly interact at level 0.05. Okay, so we follow the interaction workflow and say we do another ANOVA table. So let's say we drop out, so the interaction is not significant, so suppose we drop it out. Okay, so that this row disappears. So now we do another ANOVA table, but without the interaction row, and so this is the result. Okay, so we have one less row, interaction row is gone, and there's a few differences. Okay, so you notice there the F values, for instance, I want to point out here, the F values changed slightly for the two factors. So 18.9 became 18.7, and then 309 became 305. Of course, that doesn't significantly change their p-values. They're both highly significant. Okay, so this is the last question for prize. And so the question is, why did these give me a concise explanation for why these F values changed, and why did they only change a little bit? So type your answer in chat. Why did these F statistics change a little bit? So why are they different, and why did they change only slightly? Okay, so I think we have a correct answer there. So the interaction term is removed, and that's insignificant. So that's the first part, and then the second part was answered as well, which is that the insignificant interaction sum of squares got added to the residual, and so therefore that's going to change the F statistics slightly, but not a lot. Okay, very good. Okay, so that's a point I just want to emphasize here. So once the interaction is deleted, it looks very much like the RBD table, and so you have two rows for the two additive factor effects. Okay, so to emphasize that point, the interaction sum of squares got added to the residual because we didn't put in those parameters. And why does that make sense mathematically? Well, because there's no change to how these two, the main effect sum of squares were defined. And so because it's not significant, it's not going to add a lot to the residual, but it will change the F statistics for the main effects slightly. So in this case, since the interaction is not significant, we can interpret the main effects separately, in the sense we can just take the estimates and add them together. So we can say, okay, take the effect of that load level, add together the effect of that test level, and that gives us a good prediction for the mean of that treatment. Okay, so the final model, there's not a lot new here. We talked about it on Wednesday. So simply replaces replicates with blocks. Okay, so instead of R replicates, we have B blocks. And so just remember that these are analogous. Okay, so the CRD is analogous to a two-factor interaction model, and RBD is analogous to the two-factor interaction model with blocks. Okay, so you have the block parameters, and then the treatment parameters are again broken up into these three components for the main effects and the interaction. Okay, so this is the last slide for the review part. So R commands. So you probably have noticed up to this point that we have seen a whole plethora of ANOVA tables. So here are all the different variants of ANOVA that we can do in R, so using the AOV command. So make sure as you review, you can run through this list and you know exactly which ANOVA these commands are carrying out. Okay, so the first one, for example, is the CRD, okay, and then you have your RBD. All right, and the difference between these three, right? So A colon B, remember A colon B joins together two factors. So this gives you ANOVA for a two-factor design, which combines all the treatments together and allows you to test for treatment effects. Then you can do the interaction model. So this will break up the treatments into the three component sum of squares. And then if you can reduce it to the additive model, then it's simply A plus B. Okay, so make sure you understand all these variants of the ANOVA tables. We also showed code for how to make interaction plots and how to interpret it. And finally, we also had code for assessing model assumptions. So in the CRD case, we could do that using a box plot. And then in the RBD case, we looked at using a QQ plot of the residuals. Okay. So finally, a few comments about the final assessment. There will be more information posted online later. So just to give you a heads up, so the take-home exam, there will be 8 questions. So it'll be about the length of 2 midterm exams. So it's comprehensive in the sense it covers everything we've done in the entire course, lectures, homework, and practice sets. So in terms of breakdown, because we already tested you on midterm 1 stuff, so there will be very little on the early stuff. So 7 of the 8 problems, so 90% of it will involve the topics that have not yet been tested. And also, as noted, there will be different versions of each question. So you'll each get a random selection among the variants of each problem. Okay, so there are 8 of them, and so if you exponentiate, you realize that there is no chance that any 2 exams will actually be identical. So this will be released to you on April 9th, and then you will have 11 days to submit it. A sample exam was posted on Learn, so you can take a look at that. And also, if you need to review some of the earlier material, you can look back at the midterm 1 and 2 review slides. So the assessment will be open book, and so you can refer to anything we've done in the course, and you'll be asked to sign and affirm to a statement of integrity on the first page of the take-home, and the specific wording of that will be provided by the math faculty, and you'll be asked to affirm academic integrity before you begin. And then when you finish, you will upload your solutions to CrowdMark, same way you would submit an assignment. And so because there are 11 days for you to do that, please do not wait until the last minute to upload in case there are any last minute technical issues, and we will not accept late submissions for any reason. Same principles apply, so show your work. You don't have to simplify your numerical expressions, and you don't have to write any R code, but you should know how to read and understand R code. Okay, so that's all I have for you, and so at this point I will answer any questions you may have. So you can ask me anything, so you can fire away in chat. I'll give you a couple minutes if you want to ask me anything. Okay, so the first question is, can we write R code or do questions or do questions need to be done by hand on paper? Usually for exam questions, I will not give you the entire data set. And so generally, R will not help for that. So I might give you some summary statistics, and from there you might you would fill in or construct the ANOVA tables. And so generally you need for you to use R, you would have the full data set. So I don't expect R to be particularly helpful for that purpose. Although of course, if you want to use R as a calculator, of course you're certainly allowed to do that. Though make sure you show your work in your submission. Second question is how different is it teaching at home? Very different, of course. Certainly took a lot of getting used to talk to a camera instead of talking to you guys in person, and I certainly miss teaching in person and that kind of interaction. But I think we've been able to at least have a little bit of get a bit of fun out of it using online medium. So I certainly hope you've enjoyed it, and I've been able to get a little bit of enjoyment out of it as well, doing this with you. Okay, are there any other questions? Okay. So how will you be asking me questions? So I'll be online on Skype after this stream for office hour, and then also I will schedule Skype office hours for next week. I'll have them Monday and Wednesday. So I believe your exam will be released at noon on Thursday, and so I'll be available to chat with you on Monday and Wednesday. So I will post those hours online, and then once the exam is released on the 9th, then we will not be able to communicate until after everything is submitted. So from the 9th to the 20th, you would not be able to ask me questions. But until the exam is released, you can still ask questions, whether on Skype or on Piazza or by email. Florida stories, yeah. So those I had fun. I mean, I saw one of the memes yesterday, which was it's a lot easier to pay attention to Florida stories than Stat 32 material, and you would not be wrong in saying that. It's actually I would wholeheartedly agree with that assessment. Can I just give all of you poutine? So how many poutines would that be? So I think there are. Oh, by the way, so if you won something, send me an email so I know who you are, and then I will pick 2 more winners at random from those of you who told me your poutine preference. Okay, so. I'll post. Okay, so I will post afterwards the list of screen names that won your drink and poutine / donuts on Piazza, and then you can email me to confirm who you are. All right, so likewise, well, thanks for a great semester. You guys have been a great bunch to teach this term. And so, I don't know, we'll see what happens to this channel afterwards. I might post a random video now and then, and some of those may or may not interest you, but since I have this set up, maybe you might see other music or chess or other stuff or stats or whatever else. So And likewise, if any of you are making videos, well, let me know too, so I can check out what you guys are streaming or posting as well. So it's kind of nice to be able to share in this way, especially since we're all stuck at home right now. So let's all try to make the best of it. All right, so with that, I'm going to sign off, and we'll see you later next week, maybe in Skype or via email. And all the best for now, and we'll see you later.